Okay, let's start the journal club. So I brought a article named Metabolism-Informed Neural Network Identifies Pathways Influencing the Potency and Toxicity of Antimicrobial Combinations. So let's start from reading the abstract, find the gap sentence. So did everyone find the gap sentence? Yes. So the gap sentence is the yet currently empirical screening methods are expensive and often lead to suboptimal efficacy and inadvertent toxicity. So let me specify the gap sentence a bit. So what is antimicrobial resistance, abbreviated as AMR? So if there's a bacteria and it gets continuous exposure from to a single antibiotics, it could evolve to a super bacteria. So the super bacteria could have a antimicrobial resistance, and this could induce a severe problems in major hospitals. So there is a promising strategy for treating this problem. So it's called a combination therapy. So we use not only one, but two or more drugs together. But the problem is, once again, if we start to combine drugs, the number of combinations grows fast like this. So a pairwise case of N drugs, you could see that the cases are N choose 2 times the dosage of each drugs. But not only this, you have to consider the bacterial strain that you are targeting and the immediate condition in more cases. So the cases for testing gets it's not exponential, but it's getting really fast. It could blow off. So the prediction model for a powerful bacteria drug is demanded. But there's a question. Is it enough to develop a computational model that just efficiently kills bacteria? Is it enough to just kill bacteria good enough? Well, the answer is not quite. So the existing models are indigo, magenta, caramel. So they just find the efficient combination that could kill bacteria very efficiently. So potent means that it's efficient for killing, it's powerful. But the clinical question does not only require does it kill the bacteria? So it doesn't only require potency, but it also has to consider about, can the patient tolerate this combination? So it's about cell toxicity. And this is important for antibiotics related with liver and kidney, which is the metabolism goes on the liver, and the renal system goes on the kidney, which is a very vital system. So the desired antimicrobial combination should require two conditions: high pathogen potency and low host toxicity. So we need a framework that jointly considers the pathogen potency and host toxicity. And that is the CALMA that I'm introducing. It stands for a combining antibiotics by leveraging metabolism-inspired artificial neural networks. So like before we begin, it's kind of a long progress. So I'm going to show you the big picture first. So it starts with the omics data. I believe some of you guys never heard about omics data. So it's like a bunch of biological information, such as genomics, transcriptomics, or proteomics. It's like a set of a chemical molecule that is derived from the organism. Yes. So it basically starts from omics data, and then it combines with a genome scale metabolic model called, abbreviated as GEM. And this GEM converts the omics data into metabolic flux profiles for a single drug. But we're not just considering single drugs. So we need to have a joint feature for drug combinations, which considers the combination therapy. And then we put the features into the metabolism structured ANN, which is an artificial network. And then we get the potency and toxicity scores for the drug combination. So by using these two scores, we could prioritize which drug combinations are more efficient.
Joint feature for drug combination means we don't have data.
We have data.
For the combination.
We convert the flux profiles into features.
Okay.
So I will demonstrate it in the afterwards. So before we begin, some might ask, why is metabolism a useful bridge between antimicrobial potency and host toxicity? So talking of effect of drug combination, you can't just use chemical structure of the drug, but we need to know how the drug perturbs the cell metabolism. So for example, if a antibiotic perturbs a bacterial metabolism, such as cell wall synthesis or protein synthesis or nucleic acid synthesis, this could lead to the decrease of bacterial cell growth, which eventually leads to potency. So it's going to kill the bacteria if the cell wall synthesis or other synthesis can't work. So, but for toxicity, for drug combination, it could perturb. It doesn't always perturb, but it could perturb a host cell's metabolic pathway, especially, as I mentioned, the kidney and liver, which is functionally important. And this could link the toxicity to metabolism perturbation. So this is why we use metabolic information that could link the potency and toxicity. So how we started, I said that it starts from drug-induced omics data, but how could it be converted to metabolic flux profiles? So it starts with a GEM, a genome scale metabolic model. It's a holistic math model that reflects all the metabolic reactions that an organism can have. I can't guarantee that it has all the unknown reactions included, obviously, but it goes like this. So if you see here, this is a model system that has a biochemical network, and each A, B, C represents a metabolite, and B or V represents a flux. So if we set this system to an ODE, which is a mathematical conversion, the ODE could be written like this, but there's a typo. So the concentration of metabolic A is decreased by V1, so it's minus V1, and then it's increased by B1, so it's plus B1. So, but like I said, there's a typo. This should be plus V2 and minus V2, but I don't know why they made a mistake. But yeah. But it goes like this. So it goes for same for DB and DC. And this ODE system could be converted to matrices. Like this, we call this as the stoichiometric matrix, and V the flux vector. So it basically has a row of like number of metabolites, and the number of columns is the number of reactions. So it could, by multiplying these two, it could like reverse back to this system. So, but the problem is like we need to solve for these V. So, but like you can see, there's only 3 equations, but like seven variables. So we need more constraints here. So, like one of the most typical constraint is steady state, which is the like concentration like profile isn't changing like on like depending to time. And other constraints that are conventionally like applied to this is the flux bound. So the flux bound is like the biologically feasible flux bound, and then other constraints include nutrient availability and media condition and omics data. So this is where omics data comes here to make the constraints. And this integration is processed by IMAD, which is some kind of a optimization algorithm that helps integrate and also get the optimal point, but it's optimal flux here. Yes, it's going to be optimal flux, and then it's going to be optimal flux. So here in this article, we test 2 cases. So for E. coli, we use this kind of GM model, and this for drug perturbation data, we use this omics data. And for the M. tuberculosis, uses these kind of data. So, like to explain more, let's say that this green drug is drug A. So for this drug, we have genes that get perturbed by this drug. And then when this is integrated to the metabolic network and get the optimal flux, it goes like this. So this drug A comes here, and then there are like 7 reactions. So there will be 7 like rows here. So there will be a 1 flux vector for drug A. And here you could see that this drug A has like a color, which means that this reaction is inhibited a little bit if you like treat this drug, and it gets more inhibited when you get for this reaction when you treat this drug. But for this, you could see that the reaction flux increased. So that's how you interpret it. So the next step is, since we get the flux for a single drug, so we need to convert the individual drug profiles into combination level features.
Okay, so question is, we have omics data. that means if we give a drug, know the information how the genes are changed. How we convert it to the flux.
That is like processed by IMAT, but like they didn't specify how.
We use that IMAT algorithm
Yes,
to convert the gene expression change to the flux change.
yes.
Okay, and then I understand we got the top vector. So for each drug, we know how the flux changed.
Yes.
Then you provide that change as a constraint
No. It's a result.
result.
Yes.
Oh, I see.
The constraint is the omics data.
So top modeling work is part of the IMAP.
Yes, it's a like the IMAT also like finds the optimal flux according to the article. So this is the results of an IMAT, I think.
Anyway, the point is if we use the IMAP gene expression profile change, and we convert it to the flux change.
Yes, and we need GEM, this whole system.
Okay.
Because we're like eventually calculating the optimal flux here.
Okay. Then what is the role of IMAP?
So in the article it says like it helps integration into metabolic network and get the optimal flux.
Get the optimal flux, right?
Yes.
Why do we need a GM?
Oh, so GM is a system that has a metabolic pathway information.
IMAP can do
No, it's like I don't know how like specifically it works, but it combines the omics data and the metabolic pathway model system together, and then calculates the flux.
GM의 베이스
네.
에다가 저 믹스를 더해서
네, 더해서 한
게
예. 네, 맞습니다.
And by using IMAT, we can also specify what is the GM for this drug.
I'm not sure about that because I don't know it could do an inverse problem, but I don't know like much about IMAT, so yeah, I'll find that out and I can tell you later then. Is that okay? So we got the flux vector from a single drug, which could be represented like this. But this goes into a binary featureization. So for V positive is equal to 1 when VI0 over, VI A over VI0 is more than 2, which means the VI0 is the baseline flux. So Vp equals 1 holds when the flux here has a more than twofold perturbation. So it has a more than increase of twofold flux here, then it would like get the 1, like Vp equals 1. But otherwise it would get 0. And for negative Vn, or if it decreases more than twofold by perturbation, it would get 1. And then otherwise it would get 0. So I know that this gets kind of abstract, so I got a toy example here. So for drug A, let's say that the baseline flux for each baseline flux fold is provided for each reactions. So you could see that for Vp, it would be more than 2. It's 1, 1, 0, 0, 0, 1. And then for Vn, it would be only this dude is less than like twofold. So it's good. Only this should be 1. And this is just the binary featureization for a single drug. So we need more features to make a joint feature. So the first thing that I want to introduce is sigma feature, which is equal to 2 over n sigma v. V is the value here, and n is the number of pairs. So if you want to test pairwise combinations, the n will be 2. And another feature that I want to introduce is delta feature. So this measures the unique perturbation pattern, which means that only it like gets points when only one single drug is perturbed. One single drug perturbs a flux. So let me continue this toy example. Or here we got A and B, which is n is equal to 2. So this cancels out. And for VPA, we got this data here. So we transfer it to here. And let's say that the VP value for this drug B is calculated here. So we indicate that the sigma value for VP, which means V positive, is like this. So by meaning it's n is 2, so it's canceled out. So you just add the values here, these 2. So this should be 1, 2, 0, 0, 1, 2. And for delta feature, so it's going to be 1 if only the sum is 1. So this, so this thing is going to be 1. Only this thing is going to be 1. The other rest is going to be 0. So this, so we calculated the sigma plus and delta plus features here for VP and VPs, but we could do this also for VNs. So we have 4 features now. So this is the joint feature that they proposed. So we get 4 features per reaction.
Okay, so sigma is just anyway average. What is the delta feature?
Delta feature is like only when there's a unique
Okay.
unique perturbation.
So Boolean operator. So only one, so x1.
Yes, that's called X1. Yeah.
X1, yes. Okay. Everyone, please think why they choose this 4 feature. Why this is better than rather than just plug in the BPA, BPB. They can plug in the raw data.
Yeah, I think they could.
Like BPA, BPB. Then the raw vector, BPA, BPB.
Ah, this one.
Actually, we can plug in that.
Yeah, but I think they use this because they are going to plug in these features to neural network, and then the delta feature is kind of like I don't know much about neural networks, but I asked GPT, and then that thing said it could be a specifier that could reinforce the unique perturbation. So I'm not sure how it works, but anyways, the article just proposed this.
Any thoughts? Just think about it, everyone. Why, rather than plug in this original 2 vector, plug in this 4 feature vector, it's better for the purpose of our goal. Our goal is we find which combination of drug leads to the high toxicity and high efficacy and low toxicity. Something like that. That's our goal. the other thing that rather than plug in original two vector, this 4 different picture vector are better idea. So I think that's of course, at this point, we don't know the answer, but at least we should think.
One reason is, so just thinking about plugging the raw VPA and doing PB data
Yeah.
into the AI, and it should be like kind of concatenation.
Uh-huh.
But in that cases, we cannot, the AI do not know which relation corresponds to A and B.
Oh,
Okay. But if we compare it this way,
Uh-huh.
then at least this forces that AI focus on only the interaction between them for each relation.
Okay. So I see. So you mean the order of A and B
Yeah.
doesn't matter?
If we, yeah, or so if we just plug in raw data, it'd be no,
I see. If you concatenate
the order does not matter for them, yeah.
So what if we plug in the? I see. We have to concatenate and see
Yeah, AI doesn't know
which one.
which one they ordered
Hmm.
and
So your means explanation, if we plug in the BPA and BPV, like concatenate in the one single column vector, AI should in himself which component we should compare. But if we do this for feature, so we become more kind to the AI.
Yes.
We should look at this comparison. So we give us some advice to AI.
So the authors consider about multiple combinations, right? And combinations of multiple drugs, not just two drugs.
Yes. So the N could be more than two. So it could be applied for more than two combinations. But in this article, they just focused on two.
If so, then the delta feature and sigma feature can generalize to if you have if we have three drugs, then we need three raw features, but by making the sigma feature and delta feature, we can generalize to many drugs because neural network has fixed input size.
Yes. That's a good point. Actually, this is actually a normalized thing. So it controls the norm the size of the feature. Yes. So okay. So we get 4 features per reaction. So for this combination, we got 4 times the number of reactions as a feature. So this leads to this kind of joint profile feature processing, and the figure looks like this in the article. So it's time to feed the vector into neural network, but since I was kind of new to neural network and I'm not really still good about it, but I think it's a bit sloppy explanation, but I brought some explanations. So the input features are in the input layer. So there's a input feature vector, and this goes into the hidden layer, which is another function, such as h equals this form. And this phi is a nonlinear function. And by processing the h's, it gets out the output scores, like the prediction scores here. So by training the labels here, we get the weights, the weight matrix, and the bias vectors and all other parameters via training data. So the optimal goal here is to get the predictions close to the true value. So that's the basic concept. But what is different from just this simple artificial neural network and the metabolism-informed neural network? So instead of like, if you see here, the input features, there are only one hidden layer and you put all the inputs all together. But here, Kalma, like the metabolic informed ANN looks like this. So it says for each subsystem from 1 to n, but this subsystem is equal to like a particular metabolic pathway, such as like glycolysis or transportation. And and then we put the input features that we discussed before here. So the number of features is 4 times the number of reactions. So here we have like 8 features. So we see that the subsystem 1 has 2 reactions here. So it goes like this. And the first hidden layer decreases the neurons to the number of reactions. So it processes the reaction feature within the subsystem, which reflects a biological prior that the reaction within the same subsystem will have a biological association. And the second layer, hidden layer, it compresses to like 1. So it gets like 1 neuron per subsystem. So the output is a function of the concatenated subsystems here into the final output. So here, the final prediction could be the thing that we aimed, which is combination potency score or combination toxicity score. But this score depends on the context of how the ANN is trained. So if you use a drug combination potency label, like it's a experimental data. So if you use this label, it would predict combination potency score. And then I will introduce afterwards, but there is some kind of score that is called FEO, this weird term. So if you use this label, it would predict this score. So, well, anyways, why does the architecture have to be this way? So the first reason is that it could decrease the number of parameters. So for a fully connected ANN, which I introduced as the introduction of ANN, let's say that it has total of 6 reactions. They both have a total of 6 reactions, but Kalma's divides the reactions into subsystems. So if for each subsystem, if we assume that it has 2 reactions, and for fully connected ANN, it would have just a bunch of reactions in the whole thing. So the XI dimension the XI is again the input feature, which is 4 times the number of reactions. So the number of reactions is 6, and then you can obviously get 24. And for Kalma, for each subsystem, you get 8, because for each subsystem, you get 2 times 4. So the dimension is this. But the problem arises at the hidden layer. So as you could see, the first layer has a number of the neuron that equals the number of reactions. So here we have 6 reactions. So the hidden layer has a dimension of 6. But here, for each subsystem, we have dimension of 2, since we have 2 reactions. So if we look at this equation, this has to be 6-dimensional. So if this is 24, it's going to be 6 times 24. So it's going to have this matrix is going to have 144 parameters, while this for this case it has 2 times 8 parameters, which is 16. So it has comparably less parameters. And actually, the authors say that this really helps like decrease the parameters. Like you can see the reduction rate here. So what is the merit of like decreasing the parameters is you could like get over the overfitting problem and computational burden. The second thing is that it makes pathway level interpretation possible. So for fully connected ANN, the reaction of subsystems are just mixed all in together into the first hidden layer and then just goes out to the like, output layer. So it doesn't have two layers here. Then it gets the reactions all mixed. So it's some kind of a black box neural network. But for the Kalman ANN, it's gonna be, so if we say the output score is y hat, and you could see that it's processed by this equation, and you could see that there is a weight for each subsystem. So this z is a vector for concatenation of each z value here. So it gets the weight of how much contribution it makes the subsystem to the output. Also, we could like, I'm gonna like explain it afterwards, but there's a thing that called pathway knockoff analysis, which is you knock out all these subsystems like one by one, and then you like measure the performance change. So by doing that, you could like figure out how much contribution the subsystem each does. But I'm gonna like explain it afterwards. So, well, anyways, so is this the like okay? So we got the architecture, but how about the performance?
Is there 리액션들 서로 연관 있는 것들끼리 카테고라이즈해서 따로 학습시킨 다음에 합치는
네, 맞아. 네.
그 자르는 기준은 이미 알고 있는 거예요. 그것도 학습을 해서 분류할 수 있는.
그거는 잼이라는 그 매스 모델에서 이미 지정을 해놨어요.
그 잼이 그거죠.
어떤 식으로 리액션 하는지 그런 거에 대한 수리 모델.
맞아요. 네. 그럼
저거는 그냥 잼 믿고 하이퍼 파라미터.
네네네. 그냥 잼 따라서 하는.
이거 저자가 한국이야.
외국인. So for the model performance, so the evaluation metric is the Spearman rank correlation, which is not the like Pearson, since it's not like predicting the absolute value, but it's gonna like prioritize the ranks for like the prediction and the true. So the result goes like this. So it seems like the R value doesn't like, it's like above like 0.5 a little bit, and for this M tubular cubosis it's more low, but unfortunately this result is compared to other like models, and it's not like super good. It's not super good, but the authors say that it's okay because this like model provides two features with two things: the potency and toxicity, and biological interpretation. But like, yeah, it's not the best performance, but it says it's statistically significant. So for like potency, it's like this, but like what about host toxicity? The problem arises here for like, it's my opinion. So for toxicity, the problem is that they use the same gem-derived combination feature. Because the gem that is used here is basically knowledge on the E. coli and tubular cubosis. It's not human data. So I don't, so you could say like, why do they do this? But like they say to see how pathways influence potency and both in toxicity. And as I like said before, the artificial neural network supervised label is just changed to the potency score to this FAERS and two sites derived PR score. So I'm going to explain this here. So FERS is a acronym for FDA Adverse Event Reporting System, which is like this is a reporting system for side effects, and this is like the derived data set from FERS called two sites, which has the drug combination side effects in this database. So the PRR score is like calculated like this. So if we have the database here, and there is the contingency table. So there, the ABCD refers to the number of reports for the corresponding condition. So if there is like a report, there are cases that have a drug combination, that a combination exposure, and they do have a side effect, they would count as A. And then it would go like ABCD. And the PRR score would be calculated like this. So if you see the
You should
denomination,
explain what is drug combinations.
the drug combination exposure is like literally if a patient takes a combination of more than two drugs, and then that is just this case.
Oh.
Yeah.
Just try.
Yes, just try. Yeah.
Oh.
It's the observed data.
So drug combination exposure no means. Oh.
So you might get confused here.
Yeah. That means if the drug combination exposure is no, that means we never try that combination. How do we know there is side effect on it?
Yes, that I asked like I was also curious about that, but the combination here is accounted for just one single pair. So if there's another pair that the patient have like eaten due to like other like diseases, it could count as Q. So the PR score goes like this. So this is the ratio of side effects with no exposure from the drug combination over the like ratio of side effects in the drug combination exposure. So they interpret like this. So if this is more than one, it's like it has a more reported side effects. And the higher the PR score, the greater the toxicity. And the result goes like this. And it's not like that great, actually. But they say that it's not excellent, but like statistically significant.
Wait, everyone agree that PR is score or the side effect?
근데 페어를 먹었을 때가 맨 이쪽이잖아요.
네,
페어를 먹었을 때 사이드 이펙트가 있을 확률이
위에 거지.
위에 겁니다.
나고 다른 거는 페어 중에 하나를 먹는데 다른 컴비네이션까지 다 포함해서
네, 그러니까 그 컴비네이션이 아닌 거.
아니 다른
네,
그래도 그 해당되는 약물을 먹으면
네,
하나만 다른 거랑 컴비네이션까지 다 먹어서
그렇지.
네,
하나 먹었을 때 일어날 확률이니까
네.
두 개의 조합이 얼마나 더 사이드 이펙트의 확률을 올려주느냐에 따라
말이니까 C는 약간 베이스라인 같은 거고 A는 하필이면 그 두 개를 먹어서 더 사이드 이펙트가 커지면 두 개보다 커지는 거지. Okay.
So finally we have to choose the promising drug combinations using the scores. Although like I don't like the assumption here, but let's go on. So for pairwise combination, we get two values, which is the predicted potency score and predicted combination toxicity score. But a thing to note is that it's kind of counterintuitive that the lower the predicted potency score equals the more synergistic microbial effect, which means it kills more bacteria than is like used in individual. So it gets more synergy to kill more bacteria. So the lower score means more potency. And then for the toxicity score, it's intuitive. It's the lower score means less toxicity. So if there's a landscape, like a plane like this, we would say that this is some kind of the optimal choice. So let's see the results. So the CALMA reduces so there is a pairwise case of 35 drugs they tested. And then for each, they only tested for like pairwise of 2. So 35 choose 2 equals 595. And they just heuristically pick the combination that are both in top 75 of the potency score and the toxicity score. So it eventually like led to 18 points. So 18 combinations of pairwise drugs. So for E. coli, the blue points here are the 18 like favorable candidates that belong to like the optimized zone, and also for the M. tuberculosis. And by this, you could see that we don't need to search for the rests, like 577 points.
그러면 펜스가 is it too
Uh,
low for 펜스? 이제 아파?
I think, yeah.
Sorry, yeah.
So it's kind of counterintuitive that the lower score here represents the more synergistic biological effect.
Oh, okay.
So
So lower is better.
yeah, lower is more
Yeah.
potency. So yes. So but like, what are the red points? Since the like assumption underlying or like predicting toxicity isn't like optimal, so they actually verified using in vitro assays. So they just picked red points considering the output diversity and clinical relevance for like in vitro validation. So they want to like see if the actual toxicity is like worth to be protected. So
they use this bacteria information
yes,
to select the drug, and then they
they did
apply
yes.
human.
Yes, human cells. So they used cell line as a human in viral kidney cell. This is the kidney cell, and this is the hepatic G2 cell, which is the like liver cell. So they chose like drug combinations of various doses and went through a viability assay to like introduce it in like a brief way. It's like a measure of cell viability through a luminescence signal. So the more luminescence, the more viable cells. So by using this output, there is some kind of a program called Synergy Finder, and this calculates the synergy score. And they like tried various cases and resulted as a heat map. And this is like they didn't like. I mean, they did like represent all the cases in supplementary, but they showed that there is a best a combination that actually led to low toxicity. So here, how to interpret is like the interaction score is like actual inhibition minus expected inhibition. So if this is more than 0, it's synergistic. But here the outcome is cytotoxicity. So if higher cytotoxicity, it means that it's like toxic to human cells. And on the other hand, If it's below 0, it's antagonism. It's called antagonism, and this means that it's like less toxic to the human cell. So it reports that there is actually a case that they predicted to have a lower host cell toxicity for a combination drug. So so the final question is, can Telma tell us which metabolic pathways are associated with potency or toxicity? So as I mentioned before, there are the article says this metabolic-informed neural network is a biologically interpretable. So if there is a normal process here, normal process of getting the prediction, we could do a weight analysis, which is seeing the weight for each subsystem and judge which pathway got the most weight. Also, we could do a contribution analysis, which is for each combination, each combinations here, what pathway did the most contribution? So this time we're not only seeing the weight, but the product form here. So by using these two, we could judge how much the pathway is contributing to the prediction score. And for the knockoff analysis, we could use this system as you knock off this system and then compare the performance and directionality. What I mean by comparing the performance is that if you knock out the subsystem I, and then the performance loss drastically falls down, it means that the prediction for this case has a high contribution for subsystem I. And for directionality, it's just a metric for which did the pathway contribute to increasing the scores, or did they decrease the scores? So eventually, by using these three analysis, they say that the inner membrane the transport pathway is the most important pathway for potency, and nucleotide salvage, which is a pathway that recycles nucleotides that are used in the cells, are important for pathway for toxicity. But I can't say that this is a great strong claim, because as I said before, this is they used limited cell lines and they didn't use human-based GM models, and they didn't discuss about why the other pathways other than this could not be a conspicuous pathway that contributes. So but I do think that it could serve as a meaning for a biological suggesting a biological hypothesis. So that's the meaning. So to go to the summary, so we talked about CALMA. It's a metabolic informed feature that takes in and predicts it, makes and that makes a combination prediction possible. And the potency toxicity landscapes could somehow enable prioritization to which drug combination is more efficient. And lastly, the pathway architecture could turn predictions into biological hypothesis. But the limitations, it's not a clinically safe proof, but because it's not well-grounded. And it's not and also it's not a human gem model. It doesn't use it. And the performance is kind of not that good compared to other models. And also, since it's using neural networks, it needs more data. If we don't have data, we can't just predict any of it. And finally, the pathway signals could be hypothesis, but they just suggest association. They can't infer causality. And this is it. Thank you.